right, welcome back to Elementary Algebra. Once again, I'm Amy Fuchsteiner, your instructor for this course, and we're going to do 7.3 today. 7.3 is the addition of rational expressions with like denominators. So we are going to harken back to the skills you have from adding and subtracting fractions. And we're going to add and subtract fractions with what are known as like denominators. So when you are adding rational expressions with like denominators, again, you have polynomials A, B, and C. What that means is if you have A over C plus B over C, this would simplify to A plus B over C. Note that C cannot be 0. Our polynomials are not equal to 0 here. Subtracting is very similar. You have some polynomial A over a different polynomial C. When you subtract the rational expression B over C, again, where B and C are polynomials, this is the same as A minus B over C. And once again, no zeros in the denominator. C may be a polynomial, but it is not equal to 0. All right, let's practice some, shall we? Maybe I need the dark navy here. Okay, so for problem number 1, do we have a like denominator? Is it the same denominator in both terms? It is. And since it is, this will be the same as 2x plus 3x over 15. Since it is a common denominator, I can simply add the two numerators. So 2x plus 3x over 15. So that's going to be 5x over 15. We do want to check and see if anything will cancel. So this would cancel. The 5 and the 15 would cancel, leaving us with x over 3. First one, done. Second problem, do you have a common denominator? Both denominators are the same at 7x. So this would be the same as 2x plus y minus 9x plus 8y over 7x. But Amy, you put that second one in parentheses. Yes, I did. Because you need to remember that you want to distribute that negative. We don't just want to do any sort of subtract the first 9x and not the 8y. We are subtracting both the 9x and the 8y. So I put it in parentheses so my brain remembers that cue. So this is going to give us 2x plus y minus 9x minus 8y, all of this over 7x. When I combine these guys, I get a minus 7x over minus 7y over 7x. Oh, Amy, this one's a little bit longer. Okay. Now, you may want to cancel those 7x's. Can't do it. Cannot do it. This 7x is a part of the minus 7y. You cannot cancel. Instead, what we will do is pull out a minus 7. X plus y over 7x. I should have left myself more room. Now the 7's will cancel. I'm going to have a negative x plus y over x. Now I'm done. I cannot cancel the x's because this x is being plus to y, so I can't cancel that. The negative on the outside, I could distribute that through. I just decided not to at this point. Okay, it's not wrong if I don't. It's just a matter of whether or not that's what the instructor wants. I don't care. All right, let's look at problem number 3. Is the denominator the same? Yes, it is. So this is equal to 4x minus 3 plus x minus 7 all over 7x minus 14. But Amy, you didn't use parentheses this time. Nope, because that's addition. And addition doesn't require the parentheses. Subtraction would. I could put them there each time. I could always use the parentheses. But when you're adding, nothing changes. When you're subtracting, then you need opposites. So, all right, so what's this going to be? This is going to be 5x minus 10 over 7x minus 14. Do you see how the 5x minus 10, do you see I can pull a 5 out of both of those? I saw that. So because I could pull that 5 out, I'm going to check this one. 7x minus 14. I could pull a 7 out, and then I'm left with x minus 2. Oh, Lordy, I got an x minus 2 in both of them. That's just like what we were doing last section. So I can cancel out those x minus 2s. And I'm left with 5 over 7. Okay. Perfect. I'm feeling a bit more confident. Can we try number 4? Oh, it's subtraction. Okay, no, I'm not going to panic. The thing about subtraction is I need to remember to put the one that comes after the sign in parentheses. So this is going to be a 2n plus 1 minus n minus 4. All of this over n plus 5. Now, I have the subtraction because I want to subtract both of those. So that'll be a 2n plus 1 minus n minus a minus 4 all over n plus 5. I'm just learning to write smaller. 2n minus n is n. 1 plus 4 is 5 all over n plus 5. This is the same as n plus 5 over n plus 5. That's the same top and bottom. Ching, ching. This is just 1. Whatever all those numbers are, when I subtract them, no matter what I put in for n, I should get 1. Sweet. I like it when it sort of solidifies down to that nice, neat number. Okay, let's try number 5. This would be a 7p minus 5 minus that 2p minus 1 needs, or plus 1 needs to go in parentheses, plus the 1. I don't need to put that in parentheses because it's plus. All of this over 5p. That's 7p minus 5. Distribute the negative, minus 2p minus 1 plus 1. All of this over 5p. All right, let's combine what we can. So 7p minus 2p, that's 5p, minus 5 minus 1 plus 1, minus 5 over 5p. Can we cancel the 5p's? Nope, cannot cancel the 5p's. This 5p is having 5 subtracted from it, so I can't do that division until I do that subtraction. But I do see 5s in both of those, so I can factor out a 5. And once I've factored the 5 out, now this is being multiplied, as is this 5. So now I can cancel those 5s, and I'm left with p minus 1 over p. Beautiful. All right, let's try number 6. It looks awfully long, but all of the denominators are the same, so that at least makes things better. So now I've got a 2r plus 1 minus 2r minus 4 plus 3r minus 7. Again, I'm putting this in parentheses because that subtraction needs to get distributed to everything in the numerator. My denominators are all the same, r squared plus 5. So this will be a 2r plus 1 minus 2r minus a minus 4, it's plus 4, plus 3r minus 7, all over r squared plus 5. 2r minus 2r plus 3r. And then I've got 3r minus 2 over r squared plus 5. 5 minus 2, yep. I can't factor anything out of 3r minus 2, and I can't factor anything out of r squared plus 5. That's a squared, so it looks like maybe it could factor, but that's not a difference, and that's not a perfect square. So I can't do anything more with that. At least not with my current knowledge base. All right? Okay, great. What do we got to do now? So we have simplified, we have added, and we have subtracted. So I think the next thing is determining a least common denominator, right? So how do we find the least common denominator? Well, we got to do two things. We got to know all the factors of the denominator. And we're essentially going to build or create a denominator that includes all factors. Okay. All right, so if I look at the two denominators in number 7, I don't know why that's happening. If I look at all the denominators in number 7, I'm going to scroll in. Don't get vertigo. Okay. If I look at number 7, r squared t is r times t. 6r is 6 times r. So to build a new lowest common denominator, I need the 6, I need the r, I need a second r, and I need the t. So that's 6r squared t. Need the 6, I need the r. That wouldn't cover that one, but now I still need that r and that t. Okay. So the LCD for problem number 7 is 6r squared t. What about for problem number 8? For problem number 8, my first denominator, x minus 7, is just x minus 7, but it should be in parentheses. My second denominator is an x. So my LCD here would be x times that x minus 7. It's got to be both of them. I can't just minus 7 because I can't create addition or subtraction, right? An LCD, a lowest common denominator, is created by multiplying. It's not created by adding and subtracting things to it. So the only way I can create a common denominator here is if these two are exactly the same or if I multiply them together. So I've got an x minus 7 times an x. The LCD is x times x minus 7. All right. Let's try problem number 9. For problem number 9, I have 3 different denominators. None of these look the same, but some of them are factorable. That 3a minus 6, I can rewrite as 3a minus 2. Right? I can factor a 3 out of that. And that 5a minus 10 will also factor. I can take a 5 out, and I'm left with a minus 2. That a is just going to be an a. So when I build my LCD, I need the 3, I need the 5, I need the a, and I need the a minus 2. This gives me an LCD of 15a, a minus 2. Right? Let's try problem number 10. Because as you can see with number 10, we kicked it up a notch. Our first denominator is x squared minus 6x plus 8. This is a trinomial. It is quadratic, meaning it is degree 2. So it may be factorable. Since the leading coefficient is a 1, I can use mental math on this. What two numbers multiply to give us an 8, but when added, give us a negative 6. For an 8, it could be a 1 and 8. It could be a 2 and 4. 1 and 8 is 9, so that's not it. But 2 and 4 is 6. I need it to be a negative 6, so that would have to be a minus 2 and a minus 4. Negative times a negative is still positive, so this would be x minus 4, x minus 2. I might have put them differently, but that's okay. That is now factored. My second denominator is x squared minus 2x. I can pull an x out of this, and I'm left with x minus 2. So when I build my lowest common denominator, I need each individual unique fraction here. I need the x minus 4. I need the x minus 2. And if I take the x minus 2, that covers that second one. The only thing missing here is the x. So this would be x. I might write it as x minus 2, x minus 4. The order will not matter because it's all multiplication, so I can build that lowest common denominator in any order I want. Right? Okay. The third goal in this particular section is to build equivalent expressions using the rationals. So we want to build up the fraction, in effect, multiplying it by positive 1. So if we have a over b, these are each polynomials. A is a polynomial, b is a polynomial. If I multiply, I don't want LCD. Hold on. Let me do that again. If I have a over b, I want to multiply each of these by a new polynomial. That still builds it to AC over BC. And it's still equivalent, right? So here's what we want to do. We're in effect multiplying by 1 because C over C is just a fancy way of saying 1. So as long as we multiply by that polynomial over itself, we're good. Okay. We want to take 30y over 5. And we want to build this so that we've got 30. Oh, no, that's 3y. Sorry, that's a 3y. So we want to build this to a 30y. Okay. So in order to go from 5 to 30, I need to multiply by 6. And where there wasn't a y, I need to put a new y. So if I'm going to multiply the denominator by 6y, I also need to multiply the top by 6y. That's where we're getting our 1. (3y) times 6y is going to be an 18y squared. And this will be our final equivalent expression. Are you able to simplify this? Yup, you sure are, because we built it that way. We built it to be able to simplify. All right, let's try number 12. Here we've got 7 over x, and we want to build this so that the denominator is x times x plus 9. Well, to do that, I need to multiply this denominator by x plus 9. What I do to the denominator, I must also do to the numerator, because I want to maintain the idea that I'm multiplying by 1. There's my big old chunky 1, right? So what do I need to have in the numerator there? 7 times x plus 9. So my equivalent expression would be 7x plus 63 over x squared plus 9x. Right? Let's try 2 more. Number 13, I have 5a over a plus 1. And I want to raise that to an equivalent expression where my denominator is a plus 1 to a minus 1. In order to do that, I need to multiply this a plus 1 by 2a minus 1. And what I do to the denominator, I must also do to the numerator, 2a minus 1. This gives me 5a times 2a minus 1. If I'm asked to multiply it through, this would be 10a squared minus 5a over, let's see, that's 2a squared minus a plus 2a minus 1. And this would be my equivalent expression with a denominator of a plus 1 to a minus 1. Number 14, we have an x plus 4 over x squared minus 5x. We want to convert this. So we have an x plus 1, x minus 5 in my denominator. Now, this one is a tad bit interesting because you do need to recognize that this x squared minus 5x is factorable. That I could take this and factor it into x minus 5. This is helpful because then I've already got the x and the x minus 5 here. And I only need to multiply this by x plus 1. I only need to multiply the denominator by x plus 1. That's the only factor that I'm missing. So I would only need to multiply the numerator by x plus 1. This gives me x plus 4, x plus 1 in my numerator. I don't know how I missed that. That's a 4. If I am asked to multiply this out so that the factors aren't there, but rather the polynomial is, this would be x squared plus x plus 4x. So plus 5x, 4 times 1 is 4, over, that would be x squared minus 4x minus 5. So that would be x cubed minus 4x squared minus 5x. There we go. And I have managed to get the equivalent expression with a denominator of x plus 1, x minus 5. Oh, there we go. All right. I'm all done with 7.3 now. We've gone over the 3 goals listed for this particular section. That is, how do you add and subtract the rational expressions with like denominators? Great, that part went nicely. Determine the least common denominator. That may take a little bit of practice for you. It could come really quick or it could take some practice. And then to build the equivalent expressions with rationals. That was also fairly straightforward, but you may need to do a little bit of practice with that as well. Again, as always, if you have any questions, please don't hesitate to reach out to me or to Julia at the Math Center. They are always willing and ready to help there. All right. Thank you, and we'll see you next time.